Okay, so thank you for the introduction. I'm grateful to participate in this event. So my talk will be about quantum batteries. It is based mainly on this work, which is a collaboration with Karen Hovannisian and Alberto Imparato. But I will also touch previous work related to this issue. So the title, which is Charging by Thermalization, a quantum battery at the verge of a phase transition, should be clear at the end of my introduction. As I said, I will talk about quantum batteries, and we consider that a quantum battery is a quantum system that we use to store energy. So this quantum system will have a Hamiltonian HS, and it will be in a state ρS, and we measure the charge of the battery by the amount of energy we can extract from the system performing a unitary operation on the system. So if by this transformation here, we reduce the energy of the system, then an agent will be able to extract the charge, right? And to give a measure of how charged is the battery, we say that we look for the optimal unitary operator, so the one that decreases the most the energy of the system. And this quantity is called the ergotropy. So we will use the ergotropy to quantify the charge of the battery. And I come back later to details of the ergotropy. The important part is that this how we measure the charge is by the energy one can extract in these unitary operations. So quantum batteries has been discussed from some time now. Most of the interest has been in batteries which are formed by many entities, which can, in the charging or discharging process, they can be correlated, quantum correlated, and therefore one uses these properties of these states to charge a battery fast or to charge it with little more energy, etc. And so there are many very interesting topics related to these questions that started with this reference here. But I will not discuss about these topics. My focus will be on the following. So, as I said, the nice properties of quantum batteries are based on these delicate quantum correlations, which need a lot of control, because to keep them, you have to keep isolated the quantum system. But there is always an environment. So this environment will make that these quantum effects could be lost, and the charge could also be lost to the environment. So we thought about what about considering equilibrium batteries? So is it possible to have a battery, so a system which is in equilibrium with the bath and which will be anyway useful as a battery system? So if this is possible, then it is nice, because the system is robust, so equilibrium is very robust. We don't need any or much control to keep it in the equilibrium state. The charge is not lost because it is in equilibrium with the bath. And to charge it, you just let the system to, again, relax to equilibrium. So it will be very nice. And so this is the part of the title, charging by thermalization, right? If this is possible, and the idea is that I will try to convince you that this is possible. So the questions that will guide my talk are two. So are they possible? This is the first thing I would like to do, to argue that they are, and how we will manage to make them work. And the second question is there any quantum effect that presents some advantage? So if are there, because in equilibrium, everything could be similar to a classical case, and we wonder if there are some quantum effects that we can use with some advantage. So after discussing these two questions, I will introduce an example. The example is a system that presents a phase transition, and we will see that this quantum effect mixed with the phase transition has very interesting so the example presents very interesting properties due to those two facts. So okay, so that's the title explanation. So now, well, I'm not sorry. Okay, so yeah, so why my first question was not trivial for us? Well, because a quantum battery looks to contradict the second law of thermodynamics, right? It looks like to contradict Kelvin's statement of the second law, because we want to extract energy from a system that is in equilibrium. And this as a mathematical statement, what we know is that by this unitary process that I was mentioning in the slide before, we cannot extract energy from a system which is in the Gibbs state, right? So let me, so this property, so I forgot to mention here before, that when we are able to extract energy, so states rho s, which allow us to decrease the energy with some unitary process, are called active states. And if there is no unitary process that allows to decrease the energy, then rho s is called a passive state. And the Gibbs state is a passive state. So we cannot really use the energy of a system in the equilibrium state. So let me discuss the link between the second law of thermodynamics and the passivity of the Gibbs state. So I will consider the following thermodynamic cycle. So it has 3 steps, 1, 2, 3, and then the 4th step, we come back to situation 1. So we close the cycle. And it is a very simple cycle. We consider our system, which will be the battery, in equilibrium at a given temperature T. So then we disconnect the battery and we perform this unitary transformation, which change the energy in this amount delta E. So delta E is the final energy minus the initial energy. And then we take the system in this state and we put it again in contact with the thermal bath, and we wait for and we wait that the system relax to equilibrium. So we come back to step 1. And the second law implies that the total work done in the process, which is just this change of energy, must be positive, right? So therefore, the second law is saying that we cannot decrease the energy of this equilibrium state with this unitary transformation, right? Because we can only increase the energy. Therefore, this is not useful as a battery, but the important point here is that we are in a weak coupling regime. Why? Because we didn't consider the energy cost of disconnecting the system here from the bath or connecting the system to the bath. So this is a way to escape this condition, as I show in this picture here. So if we are now with our system is strongly coupled to a bath, then to disconnect it from the bath, we have to pay some energy. Then we change the energy of the system here. We connect it again to the bath. We will have to pay some energy to do that because we have to turn on an interaction. And then we wait for relaxation. So the total work performed on the cycle is the sum of these three quantities. And if the sum of the connection and disconnecting work is positive, then it is possible to have delta E negative. So delta E negative is allowed by the second law in the strong coupling regime, right? And this will be the focus of my talk. So the example will be in this case, but I want to show you another possibility, which is a possibility that can be done if one is able to engineer the interaction between the system and the bath. In this case, we don't have to pay any work to disconnect it. It is also a weak interaction. We change the energy of the system, but to reach equilibrium, this will not happen spontaneously. You will need to do some work to reach equilibrium. And therefore, the total work performed in the cycle is the sum of the energy change in the system plus the work for equilibration. And this also allowed to build a battery, right? And in this paper, I construct the process, and I can talk a little bit about that if there are questions about this. So now I want to focus on this step 2, which is the way that we characterize the charge of the battery. Okay, so as I said, delta E is was the energy change, but now we will focus on the extracted energy, so which is defined with a opposite sign, right? So if delta E is the energy change of the system, the energy that we can extract is minus delta E. This quantity is called ergotropy when we look for the unitary process that gives the optimal energy decrease. So the one that, otherwise the one that maximizes the extracted energy. So this quantity was discussed in this paper. It was shown that it has an explicit formula given in terms of the initial state, ρS, which I write here, it's spectral decomposition. And for this formula here to be valid, the eigenvalues here of the state has to be written in a decreasing order, while the eigenvalues of the Hamiltonian of the system has to be written with an increasing order. So with these two way of writing the state and the Hamiltonian, you can show that this is the ergotropy, the maximum energy you can extract from the system in this state. And the unitary that allows you to extract this amount of energy is given by this expression. And it's very degenerate. I mean, there are many unitaries because you can choose the phases here the way you like. Usually, because the ergotropy does not depend on the value of these phases, you will see that this exponential is replaced by 1. Equivalently, you can say that all these theta variables are fixed to 0, right? So how do you implement this unitary process? Well, you can think that you have a Hamiltonian and you make a time-dependent external potential that you change from an initial value equal to 0 to, again, a final value equal to 0, because the Hamiltonian of the battery has at the beginning and at the end of the process has to be the same. That's why these unitary transformations are called cyclic unitary transformation. Yeah, and the way that a passive state looks, so remember, passive states are states that for which there are no unitaries that allows you to decrease the energy. These states are diagonal in the eigen energy basis, and the higher the energy of the eigenvalue, the lower the population. So like the Gibbs state or any state in which the populations decrease, these are passive states. And the passive state that you get after you extract the ergotropy is given by the populations of the initial state, because a unitary operation does not change the eigenvalues of the state, and they are ordered in a decreasing way with the increasing energy. So like in this plot here. Okay, so that's what I wanted to say about the ergotropy, which, as I said, is the way that we quantify the amount of energy of our battery. And now I want to discuss with a little more detail the cycle that we use. So in the cycle, we will use the following. So we have the battery, which is strongly coupled to a bath, but our bath will have two parts. A finite part that we call the charger, and the charger is connected to a super bath, and the interaction between the charger and the super bath is very weak. So to disconnect the charger from the super bath, we don't have to pay any, there is no energy cost in disconnecting the charger with the super bath. But there is a cost for disconnecting the battery from the charger. So the cycle is the following. We start with the total Hamiltonian given by this sum. So HB represent here the Hamiltonian of the bath. Then we disconnect the of the charger. We disconnect the interaction. We have this Hamiltonian, and therefore the energy cost for disconnecting is given by this expression. So we do this very fast. For this talk, it is done abruptly. It is important to do it very fast, because if one turns off this interaction slowly, at some point, the interaction will be weak, and therefore the battery will be in the give state. And if it is in the give state, it is that state is passive. We cannot extract the energy, right? So we have to do it fast. Then when the battery is disconnected, we can compute the state of the battery by tracing out the bath from this global state, which is the global equilibrium. And express it, and we express the state of the battery as the reduced state. And here we perform the unitary transformation that extract the energy of the battery. So this is the step that one do when the agent that needs the energy will do this step. And after that step, we connect it again to the charger, with some energy cost that I will give in the next slide. And then we wait for thermalization, and the battery is charged again by the heat that flows from the bath to the battery. All right, so this is the cycle. And we can view this cycle from the perspective of the total system like that. So we start with the global equilibrium state. Here in this step, we disconnect the battery from the charger. Because this is done very fast, the state does not change. So it's so fast that the state doesn't have time to change. So the global state is the same, but the energy we pay to disconnect is given by this expression. Then we extract the energy with this unitary, right? That depends on this phases theta. So here I put this theta that will become important later. So this is a global unitary which affect the battery and the charge, which after extracting the energy, it is in this global state. And then we connect. And when we connect, so we turn on very fast again the interaction. So the energy we pay to connect is this one. And then the battery is connected to the charger, and we wait for thermalization, right? So, so this is the cycle, and we can define an efficiency, which is the energy that we extract divided by the cost to run the cycle, which is the sum of the connection work plus the disconnecting work. And it's easy to see that this, due to the second law, this has to be positive, but smaller than 1. Now, the important thing is that because this unitaries depends on these phases theta here, the connecting work will depend on these phases. And this allow us to choose in the best way that we can the value of the phases that appear in this unitary to optimize the efficiency, right? And as I will argue in my next slide that this is a quantum effect, which is not present in a classical description. So the argument is the following. So the unitary, here's, I write the unitary with these phases which are arbitrary, but for the sake of the argument that I will present here, I will consider that these phases are proportional to the energies, right? So this is just to make my argument simple here. In our paper, we have a general derivation, but the simplification that this brings about is that now we can see that this is just the bare evolution of the battery with the time theta and the unitary with the phases equal to 0. So where this term is equal to 1. And therefore, when we compute this connecting work, we replace here this unitary by this expression, which is just, as I argue here in black, is given by the expression here. So I plug this inside here, and because the cyclic property of the trace, I can write it in this way, right? So I replace this here, and then I take the dagger. So this transpose the exponential with the U0, and then I move the exponential to the left. But then you see that when the Verge system Hamiltonian does not commute with the interaction, this connecting work will depend on this phase theta. And we also need that this state keeps the correlation between the system and the charger, right? So, but the important point, so the emphasis is on this non-commutativity, which is needed for the dependence of the connecting work on the phases, right? So we have here a phase which is trivial from the local operation because this does not change the energy that the agent is able to extract from the battery. This unitary is performed on the battery when the battery is disconnected from the charger, but anyway, the phases have an effect on the global energetics because even though the battery is disconnected from the charger, it is correlated to it, right? So, okay, so this is the quantum effect. And we want to now discuss this cycle in an example. So let me here summarize a bit and present an alternative cycle which does not present the advantage. So the cycle I discuss is this. Disconnecting energy depend on the phases. Something that you can consider is to change at this step the process and say, okay, I have I extracted the energy from the battery. My battery is in this passive state, and then I connect it to a fresh new environment. So a new charger which is in the thermal state. Then if you do this, you lose the dependence on the phases, right? So it is crucial to connect to the charger that was correlated to the battery. In the example, I will discuss the situation I'm talking here about. This state is a thermal state, but the argument works more generally if this state is, so what we need for this to be useful is a global passive state, easy to prepare or given to us, and that the reduced state is active so that you can extract energy. This is what you need to build a battery. And the cycle will be closed by this preparation step that we assume that is not difficult or does not present a cost that we have to put into the budget for the efficiency of the engine, of the device. So why do I mention this? Is because in the example we will work, as I said, we will work with the thermal state, a thermal state at 0 temperature, but in the example, at the ground state of the system will be the generator. There will be two ground states, and the thermal state at 0 temperature will be this mixture of the ground state. And therefore, we will also consider that we can start the global system in one of the ground states. So this pure state given like this, which is not a thermal state, but if it is possible to easy to prepare, it is interesting to discuss this situation. Okay, so the example is the transverse-field Ising chain. So it's a chain of spin 1/2 with this Hamiltonian. So this is the Hamiltonian for the battery and the charger. So it's the total Hamiltonian. This Hamiltonian is known to present a quantum phase transition. So if we consider as a order parameter the longitudinal magnetization, it is 0 if F is larger than 0.5, than 1/2. And for values smaller than 1/2, it can take a positive value. So this will be, this is one ground state, or a negative value in the other ground states. So these are the plus and minus ground state. Please do not make attention to the colors. Just here follow the black lines. And this magnetization is characterized by a critical exponent here in the vicinity of the critical value F equal 0.5, given by this exponent. So this, as I said, is a property of the two degenerate ground states, which appear in the limit of infinite size, right? So this is the global system. For the numerics, we treat a system with periodic boundary conditions, right? So like we are in a ring, so this is closed. And the battery is a part of the chain. So for instance, in this example, this is the battery, which is here connected to the charger. but when I disconnect, I turn off the interaction between this spin and this one, and also the interaction between this spin and this other one, right? So these are the interaction energy. This is the interaction energy V, and for this battery composed of 3 spin, the Hamiltonian of the battery will be this one. So the magnetic, external magnetic field for the 3 spins of the battery, plus the 2 interaction terms between the spins that form the battery. Okay, so when we consider this system, first I will show you that if we start from a thermal state for the Ising system, so for the full battery charge system, the reduced state of the battery is active, so the ergotropy, there is a positive ergotropy. So this is what this plot shows. So the ergotropy, this is ergotropy as a function of F for a battery of 2 sides, then for a battery of 4 sides, and then for a battery of 6 sides. The full, so this is numerics, the full battery charger system has 11 spin, I think. And we see that the ergotropy peaks near the value F equal 1/2, so near the critical point. So as I said, the efficiency depends on the value of these phases theta. And here I plot the efficiency for the case that is, which is already optimized. So I will show next non-optimized efficiency, but here it is already optimized. So we can, for the M equal 2 battery, we have a quite large value of 0.5. Now, for these larger batteries, you see that the efficiency changed a little bit abruptly, and this is because it is a difficult numerical problem to find the optimal, to find the phases that optimize this quantity. So yeah, so that's why we see this like abrupt changes on the efficiency as a function of the magnetic field F. Okay, so this was a numerical evaluation for a thermal state at temperature equal 0.1, and now I will discuss a situation that we can advance a little bit analytically, which is the case of a single spin. So the battery will be just a single spin. So
Philip, can I?
Hamiltonian.
Sorry,
Yes?
Philip, can I ask a question?
Yes, please.
Yeah. So in your previous slide, if you can please go. Yeah. So the efficiency, it looks like. So am I correct if I say if you have like if you're increasing the size of the battery, the work cost for connecting and disconnecting for small size is more, because essentially the efficiency is quite small, although the ergotropy is high, let's say for M equal to 2. So essentially the work cost is more for to connect and disconnect the small units compared to M equal to 4 or 6. Is that
yeah?
Right?
So this part here depends on how the ergotropy decrease, and also how the work decrease. So it is like these typical limits in engines that you know, the cost decrease, but also the gain decrease, and it depends on how they decrease to get these exact values. But yeah, this is what I would be able to say.
Thanks.
Okay. Yeah. So now, okay. So as I was saying that I will consider a single spin battery. So the Hamiltonian of the battery is this very simple Hamiltonian, and the Hamiltonian of the interaction is always the same. We turn off and on the interaction of the spin with the neighbor spins of the charger. But I will focus now on the situation that the state of the chain is on one of the ground states, right? So it's yeah. So the global state is a pure state, and it is one ground state of the infinite Ising chain, right? So this is for the case that we can do some analytical computations. So yeah, so for the when the spin chain is in the ground state, the magnetization, so the average magnetization in the ground state is known. So for instance, the magnetization in the x direction is given by this curve I showed here before. There is an analytic expression for the magnetization in the theta direction, and the magnetization along the y direction is 0. Therefore, the reduced state of the battery, so it is a qubit, a spin 1/2 system, can be represented in the Bloch sphere, and the state is given by this expression. So these average values are well known. So if I compute the average energy of the battery is given by the magnetization in the theta direction, but the state, so this state point in the Bloch sphere, so the y component is 0, so I have this Bloch circle, and it's pointing in this direction. And we know that the passive state has to commute with the system Hamiltonian, right? So because the passive state has the same energy basis that the system Hamiltonian. So the passive state has to point in the theta direction, and unitary operations on the Bloch sphere are just rotations. So what we do is we rotate this vector to the theta direction, and this is the passive state. So now the energy of the passive state will be smaller than the energy of the active state because of this minus sign here, and because this vector, or the component, the theta component of this vector is larger than the theta component of the green vector. So this is the ergotropy, the extracted energy, which is positive. And this is the unitary that rotates the vector, and therefore is the unitary that extracts the ergotropy. But as I mentioned before, there is a phase theta that appears in these unitaries that extract the ergotropy, and the phase theta in this example is very simple. We rotate around the theta direction in an angle 2 theta. So the unitary operator representing this rotation is given like this. And therefore, these are the this is the family with theta of unitary operations that extract the ergotropy. So you see that the phase is really a trivial phase here for the battery. Now, when we plug this into the disconnecting and connecting work, we obtain these formulas where you see the dependence on theta for the connecting energy, right? So this connecting energy depends on theta, and therefore we can optimize the efficiency by looking for the optimal theta. Yeah, and so also you should notice that the connecting work and disconnecting work is given in terms of this average magnetization. So sigma, the average in the x direction is known, the average in the zeta direction is known, and this correlation function is also known in the ground state. But this one is not known analytically, right? So what we do is that we do some numerics and try to obtain this numerically. So this will be important in my next slide. Okay, so this is the ergotropy for the single qubit battery, single spin battery. It behaves around f0.5 in this way. So it presents this critical behavior. It reaches a maximum, so near f0.5 at the left. There is no ergotropy for f bigger than 1/2, because for f bigger than 1/2, there is no component on the x direction of the magnetization. So the state is passive if this is 0, and this is 0 for in the ground state when f is larger than 1/2. So this explains this part. And these are the efficiencies for different values of theta, right? So and this is so we have computed in 2 different ways the efficiency. One is by a DMRG code, and the other one is by diagonalizing the system with 11 spins. And we see that the efficiency behaves very differently if we are in the non-optimal thetas, which are finite thetas, or if we are in the optimal theta, which is theta equal to 0 in this case. So the critical behavior of the efficiency changes. From in the non-optimal, we are quite sure that the critical value is like the ergotropy with this power 1/4. In the optimal, as I said, we have to resort to a numerical evaluation for these correlation functions here. And the best fit predicts that for the optimal efficiency, the critical behavior will be 1/16 around this critical point. So we see here a very interesting game between this quantum effect, which is the possibility of choosing these phases, because these phases play a role only when there is non-commutativity between the interaction and the per Hamiltonian, and the phase transition of our battery charger system, right? So with that, I will conclude. So the important messages are that equilibrium state for strongly coupled system can be active and therefore useful as batteries. So for a quantum battery that work in this scheme, there are local phases which have consequences for the global energetics, which is a quantum feature that exists only when we have non-commutativity, or as I said here, it disappears when the Hamiltonian commute with the interaction. And in our example, with the system battery charger that present a phase transition, we see that the figure of merits of the battery increase near the phase transition, and that there is an interesting game between the phases, these quantum phases, and the phase transition for the values of this figure of merits. So with that, I want to thank you for your attention.
Thank you, Felipe. Questions?
Hello.
Hello.
Yes, Archok.
Hi, Felipe. Yeah, I mean, this is extremely interesting. So, I mean, but I missed at one point, I slightly missed. So, do you have two unitaries here? Like one is for extracting work, one is again for connecting, or no, they are just one?
No, so okay, let me, oops, sorry. Yeah, so connecting and disconnecting are, so the unitary is just for extracting the energy. So to disconnect, what we do is, yeah, it's also from the point of view of the global system, is a unitary operation, but it's very simple. It's just to, so for connecting is, oops, went too far. Yeah, so for disconnecting, we just turn off the interaction. And then for connecting, we turn it on. Right, so these are two operations which are global, let's say, and because it acts, we have to act on the system and charger. But the other unitary is the one that we use to extract the energy from just the battery here.
No, I mean, there was, you had one slide with like two things, like one had some quantum advantage, another one did not have. I mean, that is.
Okay, so maybe you are talking about here. Or in the example.
Yeah, here. So what is the difference between the upper one and the lower one, actually?
Okay, so in the lower one, so here we already, let's say, we disconnect, we extract, and then we connect, but we connect to the same charger. So, and in the in the one below, we connect to a new charger, which is in a fresh thermal state. And because in this case, there is no correlation between the battery, which is in the passive state, and the charger.
So then what is the role of the super bath then, actually?
So the super bath is just play a role here at the end to to change this state to a new thermal state. I mean, it's an auxiliary. Yeah, at some point, I mean, it's not very important. It's important just in this final step if we want to restart the cycle. But we can also think that this global state, if the battery charger is large, this will, the local states associated to this global state will look again like thermal. If you, I mean, if we believe that there is something like self-thermalization due to the unitary time evolution of the system, then you can restart again from this state. But as you operate again and again, of course, you will, the system will stop working because you never,
Okay.
I mean, this is not a true thermal state. So you will start to see the deviations.
So if I may comment here, I mean, the way I understood is the reason of having superbath is where you can write your row total as a canonical, right? So that's your
Yes.
kind of a starting point, right? In the
Yes.
right, okay.
Yeah.
Okay.
Yeah. But if you believe that the system is large enough and
Right.
this unit, the time evolution is complicated, maybe the global state for some purposes looks like a canonical state.
So let me ask another question, which is, you see, I mean, the row total is a canonical, and when you're doing this trace out and getting the reduced density matrix, now that certainly is not a canonical under the strong coupling. So what it is, I mean, it could be the coherences that are getting generated, or is it like some population inversion? So what kind of state that is actually getting generated?
So
is there any?
Yeah, so in general, so in this setup, it is coherences. So the and the intuition is that so this coupling term here kind of rotate the eigenbases of the Verge Hamiltonian, and therefore you will have coherences. But in this other scheme that I mentioned, so in this setup, which is discussed in this paper, what we have is population inversion.
Right, okay. Yeah, thank you.
Yeah, welcome.
Carlos?
Yes, just I don't know if I miss it or not, but in the specific case of the spin change, how does the efficiency or the maximal efficiency grows with the number of spins? Do you know that?
Yeah, so well, we know little about that. We in the so here,
Yes.
so
I see.
this is the number of spins that form the battery, but the system, the battery charger has a fixed number of 11 spins here, and the efficiency decrease as you increase the number of spins in the battery, although the ergotropy increase with the number of spins in the battery.
Okay. Thank you. Thank you, Felipe.
Yeah, welcome.
Philippe, I have one naive question. So this cycle that you have, this cyclic process that you have constructed, so can one construct similar cycle for classical systems and also do the same procedure?
I guess so. Yes, I think that it also works for classical systems. I think that the quantum effect that we have here is related to these phases, but otherwise it should work in a classical setup.
I see. More questions? Okay, so if there are no more questions, let's thank Philip once again, and both the speakers, KG and Philip, both. Let's thank once again.
Thank you.
Thank you.